Oye, Nyolota. So, we're going to take a look. This video is a combination of several other videos, though I may have parts of them built in, but not necessarily all of them. But the point of this is to actually do a rundown for preparation for our upcoming Qualifier Round 1 for StellarXplorers Season 11. Now, we've been advised to get teams prepared with a little bit of knowledge. I've got 4 items on my list that we were suggested to prepare our teams for. So, figured I'd put a video together that addresses that. The first 3 we're going to look at directly in this part of the video, and then the last one I'm going to bring up. I've actually made a longer video that I've been putting off for a while and decided to front load, and is now on the ISAT website, but I'll make certain that you can see it in this video. My goal is to actually stitch them together, but it will have a permanent home on the ISAT website. But let's jump in. One of the things that I've done is I brought up one of the scenarios that if you and your team have not taken a look at, you might take a look at because I think it has some applications that could be helpful for QR1. This one is ISAT 1C3. It is the 3rd in our installment of the C series for QR1, and it deals with a variety of different sensors, different scanners. Now in this one, our goal is to actually see which of 3 scanners, because you're actually given an option of 3 different ones that you could focus on, and that's one of the things that makes this a little bit more complex, to try and scan a nature preserve that has penguins on it, Danger Island, back over here. Now, the setup on this for this particular scenario is these 3 sensors, Otis 1, 2, and 3, have different limitations on them for range, and they're also thermal imagers, so they do not care if the target is in sunlight or in darkness. That may change depending on some of the other targets or scenarios that are set up. So be mindful of how things are limited based on what you're trying to do with them. Another one in the series, ISAT 1C2, Sentinel's Blind, has a camera, and that's one that it becomes important to make certain that your target is in daylight and within a given range. But the key things that we were recommended to have you take a look at. The first one is access times. Now right now, I want to find the access time not of my satellite with my target, but instead with one of the sensors. Because I don't care if the satellite can see danger islands. The satellite itself doesn't have the thermal imaging capability. It's actually the Otis scanners that we can see when we zoom in a little bit. We've got a little spotlight for our sensor. Now right now, let's say that I'm looking for, I don't know, Otis 1. I can right click on Otis 1 and go to Access. My target is Danger Islands for Otis 1. So I'm going to click Compute. And I'm running out of room here. One thing that I'm going to bring up is this. If I hover over the right spot, I get 2 arrows. I can drag this down a little bit. I like to keep the timeline available because that's something that can prove useful, but you're welcome to close it if you'd like by using the little X over here. But I'm going to open up a little bit more screen real estate by dragging that down. That also opens up that I can now bring up my report, my access report. Well, to no great surprise, when I got this started off, there's no signal whatsoever. Okay, well the reason for that is, and this might be related to a recent scenario that your teams might have seen, I'm trying to target something in a specific place on the Earth. And my inclination in this case is too low. My satellite is never over the South Pole. Well, that's tied to our inclination. If you take a look on the ISAT website, we've got a rundown of what each of the 6 classical orbital elements, or the modified ones, since we like to deal with apogee and perigee, control. I'm going to go over to properties for my satellite. Now, I need to go for the satellite, not for the sensor, because the sensors are on the satellite. So here's what I'm going to do. My inclination controls basically how far north and south is a simplistic way of looking at it for my satellite. And my problem is I'm not going far enough south. So I'm going to go much farther south. I'm going to take this up to maybe 85 degrees inclination. And I'm going to click Apply. I'm going to move this over to the side so I can see what I've got. But now we can see that I've now got my orbit tilted much more, and so I think I'm going to cross over Danger Islands, so I suspect I'm actually going to get some signal. Now I didn't close out my sensor report, it still says no access found, but I've got a button up here, as we've seen oftentimes before, that we can hit refresh and see if we've got any signal. Unfortunately we don't, but there could be a number of factors for that, not the least of which I didn't prepare fully. I didn't bring up my mission brief on this one, but I do know that my sensors have limited ranges. Right now, my altitude is only at 600 kilometers for my apogee and perigee. I have a circular orbit. I'm not going to go through all the ways that you could make this a better orbit. That's for you all to find out, but you might take a look at some of the lessons that we've got on ISAT. But right now, I've got the sensor report for Otis 1. Okay, well, Otis 1 isn't the only one I could look at. Let's go to Otis 3. So I'm going to right-click on Otis 3 and get its times for danger islands. Ah, I have some scan times for this one. But why do I have scan times for this one and not for the other? Well, the key to that lies in the mission briefing. One of these scanners, one of these sensors, Otis 3, is the high-powered one that gets really good points, but also requires you to be at a much closer range. When I right-click on it, I can go to Properties, and I've got the basic information on it, but what I've actually programmed in for you is down in the Constraints, and I've got that this sensor only works out to 1,000 kilometers. So this one gets close enough from time to time that it does actually scan. My satellite isn't up at a very high orbit, so most of the time it goes over danger islands, it's going to be about 600 kilometers away. Otis 1, however, when I go and take a look at that, based on that camera, it can't scan, it can't see anything if it's closer than 1,500 kilometers. Now, the idea on that is it has different optical zooms or different effects where it's basically like taking a book and holding it right up to your eyes. It's too close for you to be able to see. That's what's happening with the Otis 1. Okay, so range is an important thing for us to take a look at. And that leads us to our second item that we're preparing for. So the first item was access times, and specifically, we wanted the access times for a given sensor or scanner to our target. A number one problem that students may have encountered in a recent round in the competition was they accidentally pulled the access report for the satellite. Let's go ahead and do that. The satellite accesses the target a bunch of times. In fact, we've got almost 2,000, is that minutes? I think it's minutes, but 2,000 minutes. That would be an insane score, an incredibly high score. When in reality, when we actually look at the sensors that are doing the scanning that we want, I only have 10 minutes, and that's only on one sensor. Okay, so here's the thing. I have a hard time finding out what my range is, and that leads us to the second thing that we've been advised by StellarXplorers to actually get you all prepared for. Now that has a couple different places where you can access it, but I'm going to show you here. Let's go to Otis 3. That one has a signal, so it scans the target at some point, so I'm going to right-click and I'm going to go to Access, like usual, and I've got my stuff computed, but don't go to the reports, go one down to AER. AER, the report, A is for something called azimuth, E is for elevation, and R is for range. Now, these are technical terms, but azimuth is basically, if you're on the ground, for instance, it tells you which way north, south, east, or west that you would need to point. And so if you wanted to look at something, let's say you wanted to look at the North Star, which is directly above the North Pole, you would need to point due north, effectively. Granted, it may be a little bit off, but you would need to point effectively due north. So your azimuth would tell you, hey, point due north. Your elevation would then say, okay, here's how high above the horizon you need to look. And those are all measured in angles. So we've got azimuth degree, we've got elevation degree. If it's negative, that means, hey, look down. And then finally, range. Range is the thing that tells us how far away the thing is from whatever we've selected. So for instance, I've got the ISAT sensor, Otis 3, to the target, Danger Islands. So when it first makes contact, on 14th October 2023 at this time, it needs to point in a relative direction. Granted, northeast, southwest is a little bit different for the satellites, but it gives us an idea of which way to point, and we have a negative elevation because the satellite has to look downward in order to see it. We've got a range, here's the important part, of 661 kilometers. So here's where we can get our range information. But I've only got a couple of instances. This seems like quite a bit, but they're all about 600 or so. What's up with the others? I'm going to point this out because this was something that we ran into problems with in the past, and I'm going to show you a little bit. Let's go to Otis 1. I'm going to right-click on it, and I'm going to do the same thing. I'm going to do Access, and I'm going to do my AER report Well, it says no access found. It gives me no information. Well, that's weird because, I mean, Otis 1 might not be able to see the danger islands, but it's got to be some distance from the danger islands. I wish this report would actually tell me about that. Now, there are two ways that you can go about this. One is to temporarily, and I emphasize temporarily, break the scenario. Go to Otis 1, go into Basic, and remove one of the constraints. I'm going to click Apply, but I'm not going to close this because I'm going to need to reapply it later. Now, when I do that and refresh, now I'm getting information. I can see, oh, the range is 600 kilometers, just like the other one told me. The reason that this report shows nothing is because it only shows me the information if there's a contact. So I have to temporarily, and I can't stress this enough, temporarily remove that limitation. You might go, well, I want to remove that limitation because then I'm going to get a bunch of points. Well, you think you're going to get a bunch of points, but when I grade this, or when Stellar grades it, you don't get to just go in and say, well, my camera's magical, it can see whatever I want it to. We're going to say, this is what the camera can see according to the rules. So I'm going to reinstate that minimum. When I refresh, we have no information. So why would I even do that? Okay, but I want to try and get this thing where the range is good so that I can actually see it with this sensor. So I'm going to remove it temporarily again, and I'm going to show you what I can do. Now, the sensor is attached to the satellite, so I'm going to go into the satellite. Well, I think my big problem is every time my satellite goes by, it's at a range of about 600 kilometers. So basically, my apogee altitude, my perigee altitude are affecting that. So what if I go instead, the Otis 1 has a range from 1,500 to 2,500. So what if I bring this up to 2,000 kilometers instead? And let's see if it screams at me for my apogee. It does. Or sorry, perigee. It's the same old, same old. I just loaded this up, so we got to fix that problem real quick. It's been doing that a little bit more and more recently, where if you try and take it to a circular orbit, it screams. But it did actually accept it, so I'm going to click Apply. I'm going to go back over to my 3D view, and I can see that now I have a bigger orbit. And when I zoom in with the way that I've set this up, you can see that my closer range sensors aren't actually touching the surface of the Earth. But I think Otis 1 is. Okay, so when I do this, I can go in. I could reinstate my limitations, but I don't actually want to do that. I want Otis to Danger Islands, AER. When I refresh this, I can now see my range is in the 2,000 range. Okay, that should be good. So now, instead of having, actually, I'm going to go ahead and pull my access report. Let's go ahead and do this. Access report. And let's see what my total report is. I've got a bunch of minutes here, 109 minutes. But sometimes maybe I'm closer than is actually allowed. So I'm going to turn back on my limitation and click Apply. Now when I go back in, I'm going to refresh my access time. Okay, looks like we lucked out, and I am actually getting all 109 minutes. I could try and get my satellite in a place where I want it to be by temporarily, can't stress this enough, removing the constraint. What's another way that we could do this to try and get a report, numbers to show up in our range report that we could actually use to get closer? Well, here's where we can get a little bit more creative, but this might be more scenario dependent. Okay, so I've got it where right now, for instance, my satellite can actually be seen, at least on Otis 3, or Otis 1. Let's go back to Otis 3. So when I come over here, my access report on this one is no access found. ARE, nothing. Oh, I'm getting no information because I have no contact. Instead of removing the constraint temporarily, which is one option, but if you forget to put that back on, you might run into problems actually being able to get the info that you need to properly solve the scenario. The other thing you can do is this. Well, all three of the sensors are on the satellite. And if the satellite doesn't have a limitation, I could go in and right-click on the satellite, access to Danger Island, and get its ARE, its range report. And it will give me information. Now, I've got a whole bunch of them because the satellite can actually contact the target for much longer, but 5,000 isn't going to help me. My big thing is I could look for the closest approach on here, which gets down into the 2,000 range, which would be good enough for one of these sensors. So that's one other trick that I wanted to show you. You could, as I said, temporarily remove the constraint if your AER is showing no contacts. Or probably the safer thing to do is, if you know the thing that you're trying to get contact time or ranging from is on something else, like a satellite, then pull the AER for the satellite and your target, and then adjust your orbital parameters until it gets close enough that you can do something with it. So, we were advised to have you all know how you could get the range between two objects. So, here are a couple of ways to approach that, and if your range report, AER, is giving you nothing but zeros, I've now given you a few ways that you can get useful numbers to get that report where you want it to be. Okay, next up, we were advised to tell you to try and give you an idea on how positioning is related to UTC-G. Now, it took me a little bit of searching and an inquiry that StellarXplorers was good enough to give me the info on, and they said UTC-G is how it's actually marked in STK, which makes perfect sense. Most people that I've spoken with, including a colleague of mine who works on a modified form of the GPS system, said that they're used to working with just UTC. That's the more common notation, but both of them are actually perfectly applicable. UTC is Universal Time Coordination. It's basically Universal Coordinated Time. I think it may be in a different language. Sometimes they change the order on stuff because of the language limitations, but UTC is Universal Coordinated Time, and what that basically means is there's one time that basically all the nations got together and voted on, and we base all international time off of it. It's known by a couple of different names. In the military, it's called Zulu time. For most applications, it's called UTC, the Universal Time Code, or Universal Coordinated Time. A couple different ways that I've heard it. And then in a more civilian aspect, you may have heard of it as Greenwich Mean Time. It was originally set up around the prime meridian, and all the times in the world and our time zones are actually based off of it. I'm not going to get too far into the weeds on this, but I will say that I did dig up some lessons that I had put together in the past, and I am going to bring that over real quick here. Dear Lord, that's large. Okay, here we go. My ISAT site, the C series, I'm going to direct you to an in-depth video about it that I have just finished adding. So if you go over to General Knowledge, there is a new page called Multilateration and Positioning. This is actually a video that I had made 4 years ago or more for some of my classes where we were actually teaching a lesson on not only how the GPS system works, but how what in TV and movies, usually they call it triangulation. That's what most people know the word as, but my lesson will actually go through and tell you how that's a bit different. Triangulation is when you're using 3 angles, and what we're actually using is technically referred to as multilateration. Now there's a long video here that actually walks you through the detailed ideas on exactly how to work this, and there's a folder here that you can go to that has an activity that you all could actually play around with the ideas of multilateration and use information to actually find a position in Edmond, Oklahoma, because that's where our lesson took place. But I'm going to leave that to you if you want to look into it. In short, the video actually does a good rundown, but the positioning satellites use where each of the satellites are all sending out the exact same time, but it takes a little bit of time for the signal to get from the satellite down to wherever you are. Any GPS module actually listens to the signal coming from several different satellites at one time, and then noticing how the time is a little bit different from one to the other. Doing a little bit of math that's programmed into the device itself, it can then actually determine its location on the surface of the Earth, or even up off of the Earth. So that's the sort of thing that you can use using time codes to actually, with a little bit of math, find your location. Again, if you want a more in-depth analysis of that and a deeper understanding, go over to ISAT, General Knowledge, and our new page at the bottom, Multilateration and Positioning. Right above that, we also have a page that I added just the other day talking about orbital periods, which brings us to the last of our 4 points. Now, I will say the video is about to switch over and go into the first of several videos that I've been planning to add. I went ahead and front-loaded that, moved it to the top of my priority list, and I made that video with a presentation a little while back. It's a decently long one, but it actually gives you a lot of key pieces of information, including one of the things that was recommended to us. 1. Students need to know how to adjust the orbital period of a satellite. Well, I'll give you a preview of that. We can do a drop down. Instead of the apogee altitude, we can go to the orbital period. But right now you may be going, what's an orbital period? Well, check out the video that's about to come. On top of that, that video will walk you through an understanding of the orbits, the backgrounds on them, and in doing so, give us a clue on how we can adjust and control designing an orbit with a given period based on adjusting our apogee altitude and perigee altitude. So, either switch over to that page on ISAT or stay tuned as we're about to pick up with that. In this video, we're going to take a look at a couple of ideas, but they're all tied around the idea of orbital periods and relating those to the sizes of the orbit. Now, period is a technical term in science and physics. It is defined as the time it takes for one complete cycle, or in this case, one complete orbit. Orbital periods are an important thing to understand, especially when you're designing orbits to try and get the best outcomes that you can. Now, there are four main things that we're going to run through as steps along our way in this particular lesson. First thing we're going to talk about is Kepler's third law of planetary motion, updated with Newtonian mechanics. So there's a bit more than what Kepler actually stated, but it applies in the ways that we would want. We're going to take a cursory look at it, get some summaries of it, but I will have, possibly linked, another video that goes through a more in-depth deep dive into establishing that equation and the parts of it. Then we'll take a look at some definitions. We're going to have to lay out definitions and define some mathematical terms so that we can really understand what they mean. And then after we've set that up and seen relationships between those items, we can move on to step 3, which is going to be recommendations on some basic adjustment methods. But these can be very useful for making different shaped and sized orbits while trying to keep control over the time they take for one complete cycle, the period. And then finally, when we're done with those parts of the presentation, we're going to switch over to STK, where we'll actually see some of these recommendations in action and double check if they're working or not. Okay, jumping in. Kepler's third law basically says that the period squared over the semi-major axis cubed is equal to a constant. This was something that when Kepler realized it when he was looking over all of the data that had been collected over many years by Tycho Brahe, among others, well, mainly Tycho Brahe and his team, but when Kepler looked over them, he noticed that there was a mathematical relationship between the size of an orbit, represented by the semi-major axis, and the period of the orbit, the time for one complete orbit around the Sun. Now, he was looking at data for all of the regular planets that were available at that time. This is around the time that telescopes were starting to be invented, so it included out to Saturn, I believe, with the data that they collected. Like I said, there's a related video that I have, or some related videos, where we take a deeper dive into Kepler's third law in regards to AP physics or undergraduate level physics applications of it. But for this, we're going to stay on topic of key idea of Kepler's third law is that the time it takes to complete one complete orbit is mathematically related to the size of that orbit. So bigger orbit takes longer. And there's a mathematical relationship. It's not just a one-to-one, that if I double the size of the orbit, I end up with twice the time. It doesn't follow that. It follows a period squared and semi-major axis cubed. So that's a little bit more math that we would have to do. All right, moving forward from Kepler's third law. Now that we've established the key idea that the time it takes for one complete orbit depends on the size of the orbit, we can start to define what this semi-major axis means. We talked about what period means, but since it's mathematically related to the semi-major axis, let's take a moment and make certain that we understand what a semi-major axis is. Now, I've just drawn an oval here in PowerPoint for this presentation, so it may not actually perfectly match an ellipse, and I've estimated where the foci, which is how I pronounce the plural of focus, are located. Now, most people say either foci or foci, or maybe foci, I can't remember. But it's a combination of several different forms of Latin. I'm not going to bore you with that. Just take it that I'm going to pronounce it foci in classical Latin terms. So, foci is how I pronounce the plural for focus. A focus is an important point in the ellipse or any conic section. And for an elliptical orbit, you have two of these foci, And one of them's on one side, one of them's on the other. Kepler's first law of planetary motion says that all orbits are actually ellipses. A circle is a special case of an ellipse where the two foci are actually in the same spot, and that would be the center of the orbit. In general, the foci are important things that are applied mathematically with the shape of an ellipse, which is mathematically defined. We're not going to go into that for this particular lesson, but there's a lot more that you can learn, and likely will when you study conic sections in some of your math classes. And all of that knowledge can be applicable for getting better designs in orbits when you're actually working with, say, STK and others. Okay, so now that we've laid that out, we need to talk about the major axis. The major axis is basically the longest distance across the inside of your ellipse. And mathematically, it corresponds with a line that goes through the two foci that show up in the ellipse and through the actual dead center of the ellipse, which I've got marked here. So the two foci are marked with two blue dots, and then I've got an open circle in the middle to show the center. Now, Kepler's first law of planetary motion lays out that not only are orbits elliptical, they are objects in an orbit follow an elliptical path, it also laid out that the central object, for Kepler it was the sun, but for us it will often be the Earth. But it's whatever your object is orbiting around is what we would call the central object. Now, a common misconception is people might think that the central object would be in the center, hence the whole central object thing. But in this case, it's a little bit of a stretch. The important thing is Kepler's first law laid out that the Earth, or the central object, will be at one of the two foci. And there's nothing but empty space at the other. I'm going to leave that as something else to look into, but I want to bring that up in that orbits were a little strange when they were originally introduced as an idea, and honestly still are. But based on everything that we've seen and all the science that we've collected, we do end up with this outcome, that the Earth, or central object, will be at one of the foci and empty space at the other. And there's also usually empty space at the center of the orbit. There's nothing there, at least normally. Unless another satellite happens to be there, I guess. So we've got mainly the central object, the Earth, at one focus, and then you've got your elliptical orbit with the satellite going around it. Okay, now tying back into this, if we were to draw a line from one side of the orbit to the other, going through the two foci and the center, that is mathematically going to be our major axis. Now, it's called major because it's the big one. There's another one that I haven't described, which actually goes through the smallest distance across, which is actually perpendicular to it, so 90 degrees offset, and that would be the minor axis. You'll study that in the math classes, and it does have applications that we're not going to look at in this video, but they also help define something called the eccentricity, which is the second of our orbital elements, at least of the classical. Okay, now that we've got that set up, we can see that we have the major axis, the whole major axis, going through the way that I've drawn it horizontally here, and it goes through the two foci and, therefore, through our central object, specifically through the center of our central object, which would be the center of the Earth. In this case, that's the major axis. Semi or semi-major means that we're cutting that in half. So here is finally a representation of the semi-major axis of an ellipse. It is half of the biggest distance across. One of the reasons why we use the semi-major axis as opposed to the full major axis, they're both directly related to each other. It's kind of like the radius versus the diameter. In this case, to summarize why semi-major axis is usually used, we have a lot of useful mathematical relationships between the semi-major axis instead of the full major axis. So since it shows up in more equations and we've got it as something that is a little bit more versatile, a lot of times we will default to talking about the semi-major axis as a more important focus than the full major axis. As I mentioned before, this is actually the first classical orbital element. That's why I emphasize it so much, because it is so important for actually understanding Keplerian orbits, which is a key part of what we work with. Reiterating how it connects for you all, so that you don't necessarily have to know all of the equations and how to use them, though those can be useful. The semi-major axis is a way of describing the size of the orbit. So a bigger semi-major axis means a bigger orbit. And for our purposes, we usually move away from the classical orbital elements, and then we use a different set of orbital parameters where we control the altitude of the apogee or perigee. Which brings us to the next part. Okay, examples. So I've drawn out 3 diagrams here of 3 different orbits, all of them with the represented as the Earth as the central object, what the satellite is orbiting around. Now, I've got the center of the ellipse marked with each of these, and you can also see that I've got the foci, or this focus on the right, over here spread out at approximately the spot where I think it would be. Again, I haven't mathematically solved them. This is more representational. Likewise, the other focus is at the center of the Earth, so that's where I've placed the Earth. So in this top one, we have a small semi-major axis. I call that A1 for orbit 1. We see the satellite kind of frozen here. It's in the middle of an orbit going clockwise. The second orbit is a bigger orbit. I'm sending the satellite out farther, and as a result, we have a larger semi-major axis. A2 is bigger than A1. And then finally, we have a very large orbit here, very elliptical orbit, and we would have that the semi-major axis here, A3, is noticeably bigger than A2 and A1. Now, because of the first thing that we introduced, Kepler's third law of planetary motion, we can also safely conclude that the orbital period of orbit 1 is less than the orbital period of 2 and is less than the orbital period of 3. To find the exact relationship, we're going to have to get out a calculator and do a lot of math. So our focus here is more on the semi-quantitative understanding where we can know the differences between these and also know that they're not just linear, because that could help us in our design. The last example that I have over here is in the case of an circular orbit, the eccentricity is 0, and basically our major axis equals our minor axis, and therefore you'll end up with a semi-major axis that is just equal to the radius of the circle. We commonly deal with circular orbits, so that can be a useful thing to take a look at. Okay, so these were some examples moving forward. Relating orbit sizes. Now here's where we're going to get a little bit deeper into this and start opening the door up for us to be able to apply this in a useful way when designing an orbit. I'm going to go through a little bit of a mathematical view on this. Hopefully you'll be able to follow along, but I want you to understand when we get to the rules, basically the technique that you can use, I want to have shown you why this technique should work and does work. So first off, going back to what we just said, we have the semi-major axis, which is a key thing that we talk about in orbital mechanics on a regular basis. If you double that, then you would end up with, going from here over to here, that's the full major axis. And the way the orbits end up working out, that's going to correspond that the major axis goes from the perigee over to the apogee, or from the apogee over to the perigee, whichever way you want to describe it, but it's going to be the line that cuts through going from one to the other. It will pass through the central object, in this case the Earth, the center of the orbit, and also the other focus, and then eventually end up hitting the far side on the farthest point from the Earth, which we call apogee. If it's not the Earth, then this is actually apoapsis and periapsis, but we're going to stick with Earth as the central object because that's commonly what we work with. Okay, so our major axis runs from the perigee to the apogee. Okay, so on this, the altitude of the perigee and apogee are measured from the surface of the Earth, though. And that's honestly the one that we normally do our orbit designs with, so that we can easily say, hey, don't get the satellite any closer than, I don't know, 200 kilometers, because you're going to hit the atmosphere. With our designs, it usually is a bit easier for myself and many of my students to go through and design orbits based on the altitude of the apogee and perigee. Now that becomes problematic because the semi-major axis is measured from points defined by the mathematical curve of the orbit, not necessarily where the surface of the Earth happens to be. But, lucky for us with this diagram, we can see that since the major axis, the total major axis, goes from the perigee over to the apogee, we can imagine our altitude of our perigee and apogee as follows. So here's the altitude of the perigee. I've marked that h for height or altitude, and I've given it a sub p for perigee. Now we've also got, that one's in green, over here in red, we've got the altitude of the apogee. H for height, altitude, and A for apogee. But we can see that these are only part of the total major axis that runs from the perigee over to the apogee. The part that we're missing is the diameter of the Earth. But the diameter of the Earth stays the same. It's not like it's going to change, at least for our purposes with our analysis. And therefore, we can describe that the entire major axis is equal to the altitude of our perigee plus the diameter of the Earth plus the altitude of the apogee. Or sorry, apogee and perigee. I can't remember if I messed that up. But expressed as an equation, we've got the altitude of the perigee plus the diameter of the Earth plus the altitude of the apogee is equal to 2 times our semi-major axis. Okay, that's great. That's a visual representation, and now we've got something that relates our altitudes kind of to our semi-major axis, but how does that help us? What does that mean for us? Which is where we can expand on this. Okay, now here's how we can do some adjusting of orbits. And I've put together a diagram that's a little busy, but hopefully it can get across the goal for what we want and get you a little bit of understanding. What that equation means is we can get the same period, which is based on the major axis, technically the semi-major axis, the way we look at it. But if you keep the same semi-major axis, which happens if you keep the same major axis, then by Kepler's third law, you will keep the same period. Okay, well, here's one orbit that we could start off with. Let's say I start off with this orbit as part of my design, and it has some period t1. And I've got it where this is a very elliptical orbit. I've got a low perigee, very low altitude for my perigee. Here's the size of the Earth, and then I've got a very high altitude for my apogee. According to our equation, here's what I can do. If I adjust both the altitude of the perigee and the apogee by the same amount, adding that amount to one and subtracting it from the other. So in this demonstration, I'm making my orbit less elliptical by bringing my apogee down and my perigee up, but you could do this in reverse and actually go to a more elliptical orbit by adding on to the apogee and subtracting the same value from the perigee. But the important thing is this. So my example is, if I adjust the apogee and the perigee by the same amount, say I subtract 10,000 kilometers from my apogee. I bring my apogee down. So here it was over here, and now I've brought it down by about 10,000 kilometers. And since I've brought that down by 10,000, if I do the same adjustment to my perigee, except in the opposite direction, I subtracted 10,000, so over here I'm going to add 10,000, I will end up with a new orbit, orbit 2. But my new altitude of perigee and my altitude of apogee, plus the diameter of the Earth, which stays the same, gives me a total major axis that is this long. And I've moved this major axis, I've duplicated it, and I put it up here. I did the same thing with my original major axis, which was the small altitude of perigee, the same diameter of the Earth, and the larger altitude of apogee, and I brought them down, and now by duplicating them, you can see they're actually the same major axis, and therefore the same semi-major axis. Expressed mathematically, I'm adding 10,000 onto my perigee, adding the diameter of the Earth, adding the altitude of the apogee, and then I'm subtracting off 10,000 from that. So the plus 10,000 and minus 10,000 actually cancel each other out, and we still get the same semi-major axis, shown here with this diagram. One thing that we can conclude from this is that period of orbit 1 will be equal to period of orbit 2. And therefore, I can now set up different shaped and sized orbits. Well, I guess technically they're the same size, at least for now, and be able to design my orbital period, the time it takes for one complete rotation. Okay, now we're going over to demonstrating these skills. Now that we've laid out the reasons behind them and the method, we're going to switch over to STK to try and take a look and see if this is holding up, which, fingers crossed, it should. The first thing I'm going to point out is this. Usually, when we bring up the satellite settings, we use the drop-downs and we'll put it to apogee altitude and perigee altitude. As I said, that's a pretty useful one for a variety of reasons for designing orbits. We could also switch it to the semi-major axis and the eccentricity. Those are the classical orbital elements and the ones that are kind of the most formal way of describing all of these things. When you go into a catalog, they often actually list specifically those things. But I can also do the drop down and move it away from either of those and select my orbit size based off the period. And I've set this one to 4 hours. Now I took that screen grab from this scenario, this demo scenario that I've set up. Now, real quick, we've got the Earth as the central object. We got the sun in the background, and I just made 2 orbits that are kind of at opposite angles to one another so that we can see them. If I zoom in, we've got 2 satellites that are starting basically at the exact same spot so that we can kind of watch them. We've got ISAT, like usual, and the other satellite, I needed a name, so I'm calling it USAT, as in you, as opposed to I. All right, here's the thing. I went in, right-click, go over to ISAT's properties, and instead of the regular semi-major axis, here's our semi-major axis. It's 12,792.9 kilometers. Now that seems like a very specific number, what with the 0.9, but it corresponds to a period, because I did the drop-down, a period of 4 hours. And like I said, it's not like 4 hours is just going to be 4,000 kilometers. The numbers have some complexity that go along with them. But they do follow equations that if you know those equations, you could actually predict these without having to use STK itself. We can also go down to the apogee altitude and perigee altitude. I've got a circular orbit, so for a 4-hour orbit, I can see that I would need an orbital altitude, circular orbit, of radius, or not radius, but of altitude, 6,414.72 kilometers. So here's a way where you can go in, especially if you've got something that you want to happen on a specific time scale, you can switch it over, the controls over to period, and then just type in whatever time you want. I've got it set for hours, but you can also do the drop down and switch it over to minutes, so 240 minutes is 4 hours. I'm going to leave it on hours just because that's going to be the time scale that's going to be most applicable. Okay, I'm going to click apply. I'm going to minimize this, and then let's go up to watch ISAT and USAT. Now, ISAT and USAT have identical settings, but I've kind of twisted USAT's orbit around a little bit. So I'm going to press play, and we're going to watch them go off. They go around, and then they come back, and they both hit back at the same time. So both of these satellites have the same orbital period. In fact, if I rewind, we can see that we're starting this scenario at 1700 hours UTC, and we said that it's an orbital period of 4 hours, so we should have them finish up their first orbit at around 2100. Okay, I press play again. Let's come back around, and we can see we're approaching 2100, and they're coming back in. I'm going to take it one step at a time, and we get 2100 hours right here, and we see that they're back to where they started, at least pretty much. There might be a little bit of wiggle room with how we've got this set up, but we can see that every 4 hours we come back and complete one orbit. Alright, so that's showing the basics of this, where we can set an orbital time. Now let's check my model. I told us that we had a model that we can... Actually, let's check one other thing real quick. I'm going to go into ISAT, and I'm going to change it. What if I don't want 4 hours? I'm going to go with 8 hours instead. Apply. Now that I've done that, we're about to switch out, but our semi-major axis has jumped up to 20,307.4 kilometers. That's apparently, and an altitude of 13,929. That's apparently the numbers that we need to get an 8-hour orbit, at least around the planet Earth. Okay, going back over to our 3D view, we can see that ISAT is now noticeably farther out than USAT. And let's give this a try. I'm going to rewind. Let's go back to the beginning. They're starting more or less. They're not on top of each other, but they're in the same alignment. So we've got them set. Here we go. I'm going to press play. We watch USAT go zipping around the planet, and 4 hours later, USAT comes back, but ISAT is on the far side of the planet. But I'm going to keep letting it go. And now we've got, at 8 hours in, USAT has done 2 orbits, and ISAT has done 1 orbit. Now, this is a fancy technique or idea called orbital resonance. We're going to have a different lesson on that because that's one that's going to take a little while to unpack. But in short, this is what's called a 2-1 orbital resonance. So USAT orbits twice, that's the 2, for every 1 orbit that ISAT does. So we would describe this as being in a 2-1 orbital resonance. We'll talk more about that in one of the later videos, but those can be very useful for understanding designing orbits to get certain things done. Looked from above, I'll go back like this, press play one more time. We see USAT comes around, completes its orbit, and then catches back up. At 2 orbits, they end up back on top of each other. Okay, so I'm going to bring ISAT back down to 4 hours. We should see that this gets smaller again. Okay, so I have a smaller orbit once again, which is great. Now, the last thing that we want to do is we came up with a mathematical method, and we said that we can still get the same period. So once again, when I press play, now they're matched back up, and they come back and complete 1 orbit at the same time. In fact, because they have nearly identical orbits, at least from size and shape, they actually go the same speed at any of those points. Let's see what happens when we apply that method that we came up with, though. I'm going to go away from the period, and I'm going to go to the altitude. Okay, here's what I'm going to do. I'm going to raise the apogee by 1,000 kilometers. That takes me from 6,400 to 7,400, but I need to drop the perigee by the same amount. Let's see. Okay, for whatever reason, it didn't scream at me. I'll get the error at some point, I am sure. So, now that I've done that, I've switched out my orbit. Let's take a look at what the orbit looks like. Okay? Looking from the top down, we can see that ISAT is now a little bit closer and a little bit farther away, so I have slightly adjusted my orbit, though it isn't necessarily as obvious. Oop, that's the 2D. Let's go back over here. I can now switch over to the period, and we can see I've still maintained an orbital period of 4 hours. Well, let's double check that. Not that I have any reason to doubt STK, but both of our satellites are starting over here on the right-hand side, so to speak. I'm going to line this up, zoom in just a little bit, and I'm going to press play. Now they go at different rates, but watch, they will catch each other, once again, on the far side of the planet. And we can see every time the orange satellite orbits once, so does the purple satellite. So ISAT and USAT still have the same orbital period. Great. That method we introduced and we came up with math, seems to be working. Let's take this to a more extreme approach. Okay, this time I'm going to drop my perigee down pretty far. I'm going to go from 5,000. I'm going to drop down 5,000 kilometers, or at least I'm going to try to. Yay, it didn't yell at me. If I only drop that down by 5,000, if I go to my period is now no longer 4 hours. But I can come back over here. I dropped my perigee down by 5,000, so I need to increase my apogee by 5,000. Well, 7 plus 5 gives me 12,000. I'm going to click Apply. We're going to take a look at that in just a moment. Let's go back to the period. Look at that. Our period is back to 4 hours. Our technique seems to be working. Let's double check, though. Okay, so now we can see my purple satellite, ISAT, has a very elliptical orbit, and it's very different than the orange satellite. But we've got it where they're both starting here, side by side. Rewind. Press play. Let's watch. They're moving differently, but they both come back and complete 1 orbit at the same time. So, our technique is working. Now, this is a little bit different. I'm going to finish up this video by pointing out that many times we allow you to raise the apogee of an orbit above an existing limit by lowering the perigee by usually a larger amount. The common one in my scenarios, but not all of them, has been that you can raise the apogee by 100 kilometers by lowering the perigee by 200 kilometers. That is not based on the orbital values that you're seeing here, because as you can see, we would want to balance those out. You would raise one by the same amount that you lower the other, but that constraint is usually something to reflect fuel efficiency, or more accurately, the performance capabilities of our launch vehicles in order to get the satellite in orbit in the first place. So I want you to be careful not to conflate these two techniques, because you may be trying to apply both of them in one scenario, depending on your limitations. All right, those are the main things that we wanted to emphasize. To re-summarize, we've got, I'm going to go back to my presentation here and go full screen so that we can go to our closing screen. To summarize, semi-major axis describes how big the orbit is and is directly related to, or you could say determines, the orbital period, how long it takes for one complete rotation. When you're dealing with satellites and working with apogee altitude and perigee altitude, you can maintain the same period by moving one up by a certain amount and moving the other down by the same amount, so that you're just shifting where that line is. The last thing that I'll remind you of is a very important one. You can do the drop down, and instead of apogee altitude or semi-major axis, you can also design the orbit based around just the period. All right, until next time.